Identification of vortex structures in coaxial G. This work examines some method used to identify vortex structure in a coaxial compressible G flow, simulated by the 3D model LOS. The delta criterion, lambda 2 criterion, Q criterion, and omega criterion methods are considered among the most common local Eulerian vortex identification methods based on the local point analysis velocity gradient. Coaxial G-flow have been the subject of much research, both experimental and numerical. They contain vortex structures that play a major role in mixing and transfer. These vortex structures are often referred to as coherent. The search for a definition of a coherent structure has led to the development of the method for detecting vortex structure in flows. This method always used to better understand the mechanism present in the flow and characterize the structure dynamic to plan a possible control process to optimize their influence. This is very useful for heat and mass transfer application. In this study is aim of the work. In this study, it is proposed to apply the delta criterion, lambda 2 criterion, Q criterion, and omega criterion to characterize the vortex structure that results in the coaxial J flow of compressible air simulated by the LOS model. These criteria were used on the instantaneous velocity field to test the effectiveness of each of them. Delta criterion. Chong and al. Showed that for the flow with circular or spiral-shaped streamline, the eigenvalue of nabla U are complex. These have the characteristic equation for this tensor. The complex nabla U eigenvalue reflect a tendency for local rotation and a convergence of the streamline. The presence of the vortex. This complex value corresponds to the strictly positive discriminant delta of equation 1, strictly positive value, therefore indicate the presence of a vortex. Q criterion. Hand and all, on the other hand, identified coherent structure using the second velocity gradient invariant, nabla U only, area of the flow for which this invariant Q is positive, constitute ED for example. This eigenvalue can be obtained using equation 2 or by redefining Q from the deformation and rotation rate tensor. This expression is equivalent to that equation 2. The Q criterion measures a local equilibrium between the two types of the flow, solid rotation and the pure deformation vortex in which winding rotation take precedence over energy dissipation pure deformation, while have a positive. Q criterion purely dissipative zone will be associated with a negative Q criterion. Lambda 2 criterion. Jung and Hussein, having noticed the possible ambiguity of a simple local pressure minimum criterion for detecting a vortex, showed that it is possible to relate pressure minima to vortex structure in a symmetric way. The other started from the flow dynamic and studied the gradient of the Navier-Stokes momentum equation, which decompose into symmetric and antisymmetric part. The symmetrical part is then written in equation 8. Omega criterion. Liu and al. Proposed for their decomposition of the vortex has a rotational and non-rotational part. Omega is a ratio of the trace of the antisymmetric tensor squared to the sum of the trace for the symmetric and anti-symmetric tensor square as flow equation 9. Results and discussion. A series of the time calculations were performed for a compressible coaxial J-flow by the LOS model. The simulations were performed in the computational domain extending over the 13 dp in the axial direction and 17 dp in the transverse y and z direction. An initial double hyperbolic tangent velocity profile is defined at the domain entry to approximate the actual velocity profile of the coaxial J. The mean velocity components in the y and z transverse direction are zero. Randomly generated disturbance are imposed on the y and z transverse direction. Upper and lower boundary conditions of the sleep calculation domain have been prescribed. The domains found and rear boundary conditions are periodic. The boundary conditions at the exit of the domain are convective. A table 1 lists the main physical characteristics of the simulated J. We implemented the Ford method, delta criterion, lambda 2 criterion, Q criterion, and omega criterion on our coaxial J flow curve to evaluate the different vortex identification methods. We also examined the delta, lambda 2, Q, and omega method when the primary and secondary structure form in coaxial J transition phase. A convergence test was performed to demonstrate that the convergence calculations are satisfying the experimental measurement. The mean development of the coaxial J with a velocity ratio less than 1 seems very similar to that of the single J. We proceed to compare the results of the simulation with those of the experimental results of Boumerds and Wygotsky for a single J. Figures 1 and 2 provide the RMS axial and the transverse velocity component profile in full development region. The self-similarity state of the flow is obtained in this region, which indicates good results of this simulation. The RMS velocity of the component's profile is plotted with the profile obtained by Boumerds and Wygotsky. A very good agreement is observed between these profiles. Figure 3 shows the Reynolds tension A', U', profile. Reynolds tension opposite in scene indicate the presence of the coherent structure with the opposite direction of rotation. The expansion and the interaction of this vortex with downstream distance is confirmed by the expansion and decrease of peak in shear stress Reynolds profile. The shear stress Reynolds profile is plotted with the profile obtained by Boumerds and Wygotsky. A very good agreement is observed between the two profiles. Figure 4 is a graphical representation of the vortex structure detected by the different criteria delta, lambda 2, Q, and omega. It can be seen that all criteria correctly detected the vortex structure, also the center of the structure. The four methods have a great similarity in the identification of global vortex structure, but there are still differences in the local area. It can be noted that the longitudinal vortex connected the outside of the upstream ring with the inside of the downstream ring, which has the effect of accelerating the vortex winding. It can also be seen that the vortex structures are almost the same based on the key criterion and the lambda 2 criteria. Indeed, these two quantities are related by Q equal minus 1/2 lambda 2 plus lambda 1 plus lambda 3. This means that if K has a positive value, the mean eigenvalue of lambda is almost likely negative. Figure 5 shows the vortex structure given by the isosurface of lambda 2 equal minus 0.03 and lambda 2 equal minus 0.01 in a time step t equal 1900. Figure 6 shows the isosurface of the Q equals 0.03 and Q equal 0.01 at the same time step. Figure 7 shows the isosurface of the delta equals 0.03 and delta equal 0.01 at the same time step. However, if we adjust the threshold as shown in the figure 5a, 6a, and 7a, we can clearly see the main and the secondary vortex structure, and it is also seen that these structures are well stable. From the figures 5, 6, and 7, the problem is to choose the right threshold for the three criteria that all we use to capture the vortex structure in the process Y. It is sometimes difficult to choose an appropriate threshold for the lambda 2q and the delta method. The choice of the threshold relies on the correct identification of the primary and the secondary eddy structure. Figure 5b, 6b, and 7b give a poor representation of the vortex. Applying the omega method, figure 8 shows the isosurface of the omega equal 0.52 at the sometime step t equal 1900. It can be seen that the vortex structure are well captured with a fixed omega threshold equal 0.52 with no threshold adjustment. After a number of the threshold adjustment, figure 9 shows that the isosurface of the Q equals 0.03 and lambda 2 equal minus 0.01 really capture the vortex structure and are similar to that in the figure 8. Conclusion. There is many methods for detecting vortex structure to universally define coherent structure. The majority of this method focus on the definition of the vortices, yet none of them manage to give an objectively superior definition of them to the other. Therefore, it is appropriate in most cases to carry out comparative study and use the criterion that seem to be most consistent with the observation of the vorticity field. We found that the omega method can capture both strong and weak vortices. With the adjustment, there is no need to select an appropriate threshold. So the omega vortex identification method is valuable and is useful for the study of the physics of the turbulence and many other vortex-dominated flow. Thank you so much.